it is given that, and they give us the sine, cosine, and tangent of 70 degrees, or at least they give us the first few digits of them. And then they get into the meat of this actual diagram. In the diagram above, angle ABC and angle BCD are right angles. And they show us that right over here. This is angle ABC, angle BCD. And then they say that AC, segment AC, is parallel to BD. So AC is parallel to BD. And AB is parallel to CD. AB is parallel to CD. And all of that looks, the way it was drawn, it looks like they're parallel as well, but it's nice that they're telling us that. Otherwise, we can't really assume that. Which of the following is closest to the length of AB? And they give us some choices here. So let's think about it. So we have a 70-degree angle here, and they've given us the sine, cosine, and tangent of 70 degrees. So it feels like we should be able to use that somehow. Actually, if they were asking us for the length of side CD, we could immediately apply our trigonometry. Because for this bottom right triangle, this triangle BCD, we could apply the SOHCAHTOA definition of cosine. We just remind ourselves, SOHCAHTOA. Sine of an angle is opposite over hypotenuse. Cosine of an angle is adjacent over hypotenuse. Tangent of an angle is opposite over adjacent. Well, over here for BCD, triangle BCD, for this triangle right over here, we know the hypotenuse. We know the angle. And if we were trying to figure out what CD was equal to, well, we would need to figure out what the adjacent side is. And I could just call that lowercase a. That would be the adjacent side. So what deals with adjacent and hypotenuse? Well, cosine deals with adjacent and hypotenuse. And if any of this looks completely foreign to you, I encourage you to watch the basic trigonometry videos on Khan Academy. But we know that the cosine of 70 degrees would be equal to the length of the adjacent side over the length of the hypotenuse, over 8.9. Or if you multiply both sides by 8.9, you have 8.9 times the cosine of 70 degrees is equal to the length of this adjacent side. And they tell us what the cosine of 70 degrees is. It's 0.3420. So you'd have 8.9 times 0.3420. If we don't really need to write that last zero, and it keeps going on and on. Actually, let me just write it there. I'll just write the first couple of digits. That's going to be approximately equal to A. This isn't exactly the cosine of 70 degrees, but it's reasonably accurate. And so if we look at this, this is almost 8, and this is a little bit more, or sorry, this is almost 9, and this is a little bit more than a third. So a third of 9 would be 3. So this should be, I don't know, I'm guessing a little bit, around 3. And if you look at the choices, well, there is a choice. There is a choice that looks right around where we need. None of these other values are even close to 3. But we have, and if that's all, if we were trying to figure out the length of CD, we'd be done. I would say I would just pick this choice right over here. But we're not asked just the length of CD, we're asked the length of AB. And you might say, hey, look, the way this figure is drawn, AB looks to be the exact same length as CD. And maybe if you're under time pressure, you might be able to make that leap and just go ahead with it, and bad things would not happen. But if you wanted to be a little bit more rigorous about it, a little bit more sure, you'd probably want to prove it to yourself. And that's where the parallel lines come in value. Because what we're going to do is we're going to prove that triangle BCD, what I've shaded in blue, is congruent to triangle ABC. We're going to prove that they're congruent, and we're going to prove that they're congruent by showing that their corresponding angles are congruent, and that they have at least one congruent side, the side that they share right over here. They both share this side. So they both share that side. So let's prove that all of their angles, their corresponding angles, are congruent. They both already have one right angle, and we can prove that corresponding angles are congruent by extending some of these parallel lines, or just thinking about transversals and parallel lines. And if those words I just told you make no sense, I encourage you to watch the videos on angles and transversals and parallel lines on Khan Academy. So the first thing is, I want to see if I can establish that this thing up here, that angle BAC, that this is also 70 degrees. It looks like it, but I'd like to prove it. So one thing I could do is I could extend, let me do it this way. So if I extended this line like that, and if I extend, and I'm just doing this to help you visualize a transversal of parallel lines, and then if I extend this line like this, now you see that if you were thinking about line CD, it is a transversal across these two parallel lines. And when you look at it that way, you see that this angle corresponds to this angle right over here. So if this angle is 70 degrees, then this angle is also going to be 70 degrees. Now, if that angle is 70 degrees, now let's make AC into a transversal. So let me do something. Let me do it like this. Let me extend this line. So let me extend this just so we see how the lines intersect. And I can even extend this one. Whoops, that's not what I wanted to do. So let me extend that one a little bit. So it looks like this. And so you see AC is a transversal for the line AB and the line CD. And we know alternate interior angles are congruent. And this one is an alternate interior angle with this one right over here. So if this is 70 degrees, then this too must be 70 degrees. So now we've established this angle is 90, this angle is 90, this angle is 70, this angle is 70. Well, if two angles of a triangle are congruent, the third angle is going to be congruent. All three of them have to add up to 180 degrees. So this thing right over here, this thing right over, let me just in a different color. This thing right over here, that's going to be 180 minus 90 minus 70. 180 minus 90 is 90, minus 70 is 20. That's going to be 20 degrees. And by the exact same logic, this one also is going to be 20 degrees. 180 minus 90 minus 70, 20 degrees. So both of these triangles, all of their interior angles are the same. Their corresponding interior angles are congruent. That by itself would make them similar. But then one of the corresponding sides, we know that that is congruent. So between the angles being congruent and then the side being congruent, we know that the triangles themselves are congruent. So if the hypotenuse of BCD is 8.9, then the hypotenuse of ABC is also going to be 8.9. And now figuring out the length of AB, is exactly the same thing as figuring out the length of C is the same thing as the length of CD. These are corresponding sides. And since the triangles are congruent, the length of AB is going to be the same thing as the length of CD, which is, of course, 3.04. This is what we started solving at the beginning of the video. Now, I wouldn't normally suggest this to you, but, if you're taking a test and if you're under time pressure, there is this one actually was drawn fairly close to scale. At least the way, I don't know if you would actually see this was a sample item we constructed, but this one, well, anyway, I won't go too much into that.